lectures, we started from the question, what happens when I propagate strings in flat space? So we wrote down an action, an area action, which is essentially the induced metric for the, which was computed from the induced metric for the string moving in flat space. Now, this means that it's actually pretty straightforward to, at least conceptually, imagine how to write an action and a theory of a string moving in a curved space. After all, I can surely write a Nambu-Goto action for a string moving in flat space, in curved space, just by adding a metric. Or I can write a Polyakov action. Gauge fix the metric on the worksheet, and then study this theory. It's not a free theory anymore, but in principle, I can do that. Now, this should be strange. This should sound very strange to you, because we just discussed for 2 weeks the fact that string theory should include gravity. That one of the excitations of string theory is the graviton. So how would we ever be able, why would we ever be able to study string theory in a generic gravitational background, which doesn't even satisfy equations of motions of gravity, if string theory is really a theory of gravity? You surely wouldn't expect to be able to study Einstein's relativity in a generic metric, not even perturbation theory. So what's going on? Well, the point is that although this action is classically while invariant, quantum mechanically it's not. And it's not the usual problem of the 26 dimensions. There are further problems here. So because this is not a free theory, it's an interacting theory. It's actually not even scaling invariant quantum mechanically. So when you study interacting quantum field theories, you must have seen something like a normalization group flow. So you must have seen that when you define an action with some couplings, these couplings depend on your renormalization group scale. If you do a scale transformation, the couplings change. Your theory does not have scale symmetry. So scale invariant quantum field theories are actually pretty rare. So here, there must be some quantum mechanical trouble with this sort of action. So how do you quantify this problem?
So usually when you have a theory that's not scale invariant, it's because there's some kind of mass term, right? Or something.
No. Take QED with no mass for the electron. That's still not scale invariant, because your coupling, your normalized coupling, is a function of your scale, your normalization scale. So if you change your scale, your coupling changes. It can get stronger, it can get weaker, depending if the theory is asymptotically free or infrared free. But it will not stay the same. So in quantum field theory, you usually express this in terms of exactly the dependence on the normalization scale to some sort of big RG flow equation. Something like that. So there is a beta function which you can compute at all order in perturbation theory, which tells you how the couplings evolve if you change the scale. In a similar way, if you gauge fix the metric H, we should be able to write down some RG flow equations for our metric. Sorry for mu and mu. This is not derivative with respect of x mu. This is derivative with respect of mu. Sorry. So expect to be able to write something like that. So your theory has a chance to be scale invariant only if this beta function vanishes. Another way to express this sort of relation in terms of breaking while symmetry is in terms of the stress tensor. You can say that the trace of the stress tensor is not zero in your theory, but quantum mechanically it becomes something non-zero. For example, might acquire a contribution that is non-zero and is proportional to this operator. Yes?
I just want to make sure. So you wrote down RG equation for G here. So is that because you're treating G as a coupling, not as a dynamical field?
That's right. Here G is a coupling, right? I'm just writing the way the string will move in this background position of space, function of space, so function of the dynamical variables. But itself, this function is not dynamical, it's just given. Then, of course, there might be other pieces proportional to other operators, but let me just focus on this one. So, see, the relation between this statement and this statement is that to do a scale transformation of the theory, you can just add the stress tensor to the trace of the stress tensor to the action. And then this will modify the metric by the beta function. Okay? Now, if I just give you this and ask you to compute a beta function, that's a bit tricky. It's not a free theory, it is a complicated theory. How do you compute things? Well, typically the only thing you can do is to do some perturbation theory. So what you can do is to say, okay, I know that when the metric is flat, my theory is scale invariant, quantum mechanically. So perhaps I should try to do some sort of expansion in curvature. Because the curvature is a dimensionful quantity. You can do that by just putting introducing some dimensionful scale. See, until now I just omitted that. I was writing formula like this, which should have made you a little bit queasy. The momentum clearly is the dimensionful quantity. But I had just set this scale to 1. So I was measuring everything in terms of this scale, which is the tension of the string. Or if you want, it's related to the masses of the excited string modes, for example. So I'm going to do an expansion, perturbative expansion, which is good when the curvature of space-time is small compared to the scale set by the energy of the excited string states. So how do you do perturbation theory here? So I can pick a point in my space-time and expand. So I'm going to just study small fluctuations around some point in space-time. I can expand also the metric. Okay. And so this complicated action becomes actually, can be expanded in alpha prime. You get something polynomial. It starts with a quadratic path in free space-time. And then you get interactions like x dx dx, x squared dx dx. You do your nice perturbation theory, you do a one-loop calculation, you compute the beta function. And the result is that at the leading order, the beta function for G is this. So the leading order in alpha prime, or the leading order in a curvature expansion, the beta function is proportional to the Ricci curvature, to the Ricci tensor. So the leading order, a string can propagate in space-time only if the space-time satisfies Einstein equations. So the leading order, vanishing of the beta function for this coupling is the same as Einstein's equation for the metric in the vacuum. So things are actually consistent. Gravity is dynamical. It's gonna, the curvature, the metric will in general have to be a function of x naught if you want, and all the x's in such a way that satisfies the equations of motion. And then, of course, this is only the perturbative, the leading order in perturbation theory. You're gonna get higher stuff. And these higher corrections to the equation of motion of the graviton can be thought of as coming from integrating away the massive string modes, if you want. Or if you want that. So there is almost a theorem, not quite, that the beta functions can always be written as the gradient of something. So this beta there is a general expectation that at all order in alpha prime, this beta will be the variation of something with respect to the metric. So by just studying this computing the beta functions for this theory, higher and higher order, you get essentially the effective action for the gravity in string theory. Now, what I said about gravity, well, let me just make another statement. So now you might worry even more, perhaps. So we had discovered a graviton, a theory of gravity in the excitations of the strings, and now I have a different way to introduce a metric and a dynamical metric and a gravity in the theory. Are they distinct or are they the same? So suppose I study a small fluctuation of the gravity of the metric, for example. So I write my G at this eta plus delta G. And let's write a string theory, scattering amplitude, in this deformed background. So what do? We have our path integral over x's, path integral over ghosts, and then we have the action. So there is a standard action of the x's plus the standard action of the ghosts, plus this the effect of the deformation. And perhaps I can even expand this deformation in Fourier transform. And then have my vertex operators. Mm-hmm.
I'm trying to see if I understand. So we're saying in order for my theory to be scale invariant, I should pick my G such that R is 0.
That's right.
But to leading order at least. But then now we're saying we're going to let G be a dynamical field and invariant.
well, so I still wanted to satisfy the Einstein's equation. So so let me just take a particular example of a small fluctuation around space-time, flat space, which satisfies these equations to the leading order. So, so I'm just plugging this action inside the standard way of computing the string theory scattering amplitudes, say at 3 level. Now, you see that all that we are doing by introducing this deformation of the metric is that we are inserting a coherent superposition of many copies of the graviton vertex operator. So the scattering amplitude in the presence of that deformation is the same as what you will get just by starting with the scattering amplitude with no deformation and then adding to the original particles you're scattering 1 copy, 2 copies, 3 copies, 4 copies, and so on of the graviton vertex operator. Now, this is exactly what you would do in a quantum field theory to do scattering in the presence of a coherent state of a classical macroscopic profile for one of your fields. You just add to your scattering amplitudes no copies, 1 copy, 2 copies, and so on of this profile. Essentially, you're scattering in the presence of a superposition of this coherent state of these particles. So somehow, we started from a deformation of the theory, of string theory, a continuous deformation of string theory, and we ended up with the next dynamic, a coherent state for a dynamical excitation of string theory. So we started by putting by hand some modification of the theory. We found that modification only makes sense if it behaves just like a dynamical field. And furthermore, the effect is exactly the same as we were just by hand exciting one of the dynamical fields of the theory. Now, this observation generalizes, meaning whatever other continuous deformation you can imagine of this theory, so whatever continuous deformation of your string theory you can imagine, you can express it by adding, infinitesimally, by adding to the action of your matter field some correction term. In order for the correction term to be to preserve Wild symmetry, the leading order, it always has to be an operator of the theory, which is a primary and has dimension delta and delta bar equal to 1. It has no spin and has scaling dimension 2. So that when you insert it in your action, it doesn't break 2-dimensional Lorentz symmetry. It doesn't break scaling symmetry at the leading order. But that's exactly the same as the vertex operator for one of the states of your string theory. So every continuous deformation of a string theory can be interpreted as a coherent state for one of the excitations of string theory. So every knob, every coupling that you can introduce in string theory will always turn out to be a dynamical object and actually a local dynamical object, meaning it's the wave of some dynamical field, which can actually have different values in different locations in space-time. So this is pretty much probably the most striking property of string theory. You cannot change it from outside. Any quantum field theory has parameters. You can always add new fields, modify it, make it part of something bigger. With string theory, you cannot. What you're given with to work with is what you have. You can, every deformation you can try to do to it is actually already part of the theory. You cannot extend it. So,
So you say that the string theory in the low energy limit is quantum field theory, right?
yes.
But so where does that freedom comes from in quantum field theory? I mean, if I take this theory reduced to the low energy limit, you're saying that any deformation that I do to string theory is already contained in the theory, right?
Yes.
But for quantum field theory, I can deform my theory by hand.
That's right. So those deformations of the infrared theory do not follow from a deformation of the UV theory. Now this sort of thing can happen in quantum field theory too. If I have a quantum field theory in the ultraviolet that flows to some other quantum field theory in the infrared, the quantum field theory in the infrared might have more deformations than the one in UV. But typically they all have deformations. And in particular, you can always add some other fields. They have some very heavy fields. In string theory, you cannot. Now, so we can easily describe, for example, what is the effect on the worldsheet theory of adding excitations of the other massless fields that we discussed. For example, if you want to add a B field to your action, you do it by adding something that looks almost like that. But it's antisymmetric.
Can I ask you to repeat one thing from before?
Yes.
So where does the requirement that the beta function is 0 enter the expansion that we have written there?
Well, here you need, if you want to interpret this scattering amplitude, this better be Q closed. And this better be a string mode, a physical string mode. On the other hand, if you want to interpret this deformation of the action, it better preserve at least at the leading order while symmetry. And then you can worry about higher orders, nonlinear terms in the beta function, which come from regularizing the various powers of this coupling. But at the leading order, this has to satisfy the linearized Einstein equations.
The fact that this satisfies the Einstein equation, is that why you say this is a theory of gravity?
Yes.
So, so at all times are we ignoring, so we're saying that satisfying Einstein's equations for when we don't take into account the strings themselves?
Well,
in the sense that they should be matter, right? So
that's right. That's right. So what does it mean? So if you add other semi-classical, if you turn on give a vev to some other fields, like the B field, or what any other string state, that will modify the action further. You'll have new couplings. I'm going to write down some of them just now. That will modify the beta function. So it will introduce new terms on the right-hand side.
So I can have in principle T sub T.
That's right. So this S I was writing here will become a function of G, and the other fields that I've turned on. So I put an alpha prime there. There was supposed to be 1 over alpha prime. I'm sorry. There was something that was not working dimensionally. Okay. So you can get most of the couplings that I'm writing on the blackboard just by looking at the vertex operators for the corresponding fields. The same way as this was the vertex operator for a graviton. So it was the operator that corresponds to the state A minus 1 mu A bar minus 1 mu P. Delta G mu P. So remember the graviton came from the symmetric traceless part of this field.
So, question related to this. So you said we started off by adding a spinless perturbation, and that gave us a spin 2 graviton. So how did we get from spin 0 to spin 2?
Sorry, yeah. Unfortunately, I used the spin for both, but there is a spin on the worksheet and a spin in target space. So a field can carry these A, B indices which represent coordinates on the worksheet, or it can carry the mu, nu Greek indices which represent indices in the target. So this looks almost the same as the graviton coupling. Which is the square root of h, I forget. But except that the B is antisymmetric instead of being symmetric. So what is the meaning of this coupling? So B is a true form. You are contracting with the Jacobian of the transformation from the worksheet to the target and integrating it over the worksheet. If you have seen some differential geometry, this is something like the integral of the pullback of B to the worksheet. If you've seen some electromagnetism, this should remind you of a coupling of a particle in electromagnetic fields. So a particle couples to a gauge field. So a coupling of this form. So you have your trajectory of the particle, and you integrate A along it. That tells you that the particle is charged under your gauge field. So this coupling is a string version of that. So if you have a string, the particle couples naturally to a one form because you can integrate a one form on the word line of the particle.
Do we need to add something to that equation to make it invariant?
Yeah, I'm trying to remember. I think it looks fine.
So epsilon, but transformed.
Sorry, epsilon means, my bad. Epsilon AB, epsilon 1, 2 is 1. Epsilon 2, 1 is minus 1. Epsilon 1, 1 is 0. Epsilon 2, 2 is 0.
So
It's the totally antisymmetric tensor.
There's no square root G.
I don't think so.
Okay. So your epsilon here is a tensor density, or is the tensor itself?
I think it's the tensor itself, because essentially what this means is the 1x, the 2x, minus the 2x, the 1x. So it's clearly invariant under diffeomorphisms. And it's sort of topological. It doesn't depend on the metric on the worksheet. So it's automatically well invariant. And you can think about it as, because if you have the worksheet of your string, and you integrate B over it, integrate this two form over this worksheet. So this means that if you want a source for this B, you need to consider some nice long string. So this B field is something that is sensitive to strings that are stretched across your space-time. If you integrate it just on a little cylinder, is like a dipole charge for B. So most of your strings are like dipoles from the point of view of B. They have no net charge for B, your string states, but they still source some B. But if you want to really have a source for B, like a monopole for your electric field, like a single charge for electric field, you need to consider a string stretched across spacetime. And we'll do that probably very soon. Okay, so this is the coupling of B. We can also mention the coupling of the tachyon. That's going to be something like this. Let's go to phase there, probably not. So the tachyon behaves like a sort of a potential on your worksheet. It prevents the string from propagating somewhere. So we don't know what happens when the tachyon actually decays. So in principle, the tachyon is like it's sitting on the top of an unstable potential. So bosonic string theory is just living on the top of a very unstable location. Whatever excitation you throw in is going to make the tachyon decay, and something will happen. We don't know what, but essentially it's going to kill the strings.
I guess we haven't shown this yet, but when we're adding this B and the T, we haven't said how these guys will. There has to be some restriction in this quantity, right?
That's right. So at the linearized order, the restriction is that they should satisfy the linearized. They should be physical string modes. So the linearized order, Laplacian of T plus QT is 0, say. Okay. But of course, with this technique, you can actually find the nonlinear equations of motions for these fields. You can literally find the beta functions as a function of the metric, B, T, and the dilaton, which I'm going to describe momentarily. So the beta function for every coupling you introduce in your action has to vanish. And this gives you the equations of motion for the corresponding field. And I didn't write them down on my notes, unfortunately, but you can find them on the Polchinski. I can write them on the Blackboard if I take the Polchinski. Typically, they're written without the tachyon. Let's see if I can find them. Okay. So I thought I could find them under beta, but I was wrong. Oh. I guess not. Effective action. Yes, I thought hoping. Okay. Yes. So you usually find this sort of expressions in the textbook. What do they mean? Is that the trace of the stress tensor is as times proportional to all the marginal and relevant operators of your theory. But we are omitting the tachyon for a moment. So there is a tachyon which contains relevant operators like x squared, x cubed, x to the fourth, and so on. And then there are the ones correspond to marginal operators. The beta function that is associated to the dilaton is kind of funny. So it's supposed to see, it starts with this d-26, which shows the conformal anomaly in flat space. If you remember it, the d-26 was a central charge, was sitting in front of the Ricci curvature. I don't know if you can see it from over there. Okay. Or the Ricci curvature on the worksheet, not on targets, on the target space. So in general, people write the coupling of the dilaton to on the worksheet in kind of a funny way. So no, it's not right. I was hoping. Anyway, I'll get it back. So they write the coupling of the dilaton without alpha prime, if it's a strange coupling of this sort. Which is rather confusing from this sort of point of view, because this doesn't look like adding some vertex operator for the dilaton. Now here there are some complicated technical issues in the sense that there are some subtleties in disentangling the dilaton from the graviton when you try to, in a covariant way. Nothing serious, but they're also related to the fact that, you remember, when you look for Q-exact states, they typically get some extra ghost contributions. So at the end, what's happening is that when you move, you can move around the dilaton couplings a bit with various redefinitions or choices of conventions, and you can end up with couplings that look like this. So couplings which involve the ghosts. When you integrate this by parts, you get the divergence of the ghost number current. Which, as you perhaps remember, was proportional to the curvature. So anyway, the details are messy and usually not written in the textbooks very much also. Well, if you look at the Tolchinsky, for example, there are these sort of things discussed before he introduced the conformal gauge. Precisely because when you go in conformal gauge, you try to make things flat. You typically move your curvature away to some other patches of your worksheet. And so it's kind of tricky to see this coupling. So let's just believe for a moment that this is the case, that if you add the dilaton excitation in string theory, turns out into this funny coupling on the worksheet. Now, this is very important coupling because suppose that your dilaton was, say, constant in space-time. Suppose you turn on a constant profile of your dilaton. What is this? It's the integral of the curvature, Ricci curvature, over your worksheet. There's actually a topological invariant. It just measures the topology of your worksheet. So if you integrate the curvature over the sphere, in a probability normalization, you get 2. You integrate over the surface of donut or a torus, you get 0. You integrate the surface with various handles, you get -2, -4, and so on. So that means that the contribute of a dilaton to this path integral is just to rescale the string coupling. So originally an amplitude at some loop level L was weighted by something like g to the 2 minus 2L in perturbation theory. If you add this dilaton coupling, this become, you get an extra rescaling, which means the change in the dilaton, giving a vev to the dilaton, actually is the same as change in the string coupling itself. So this is perhaps the most striking version of the idea that there are no continuous deformations of string theory which are not dynamical. Not just the changes in the action of that describes the space-time in which your string moves, but even changes to the coupling in our perturbative expansion can be ascribed to dynamical fluctuations of some field. So there is no way, so the coupling is not a constant that you put in, just the vev of some field. It can fluctuate. You can have different coupling in different locations. Something might source this dilaton. Some dynamical process might make the coupling stronger or weaker in some location of your spacetime. So again, there are no continuous deformations. And the equations of motions. Let me see if I can make them pop out again. For this graviton, B field, and dilaton are pretty reasonable. This, of course, is a bit funny, but this, in a sense, tells you what happens if you're trying to study a theory of strings which is not critical. So if you remember, I was saying at the beginning, if you don't live in 26 dimensions, the wild symmetry is not a symmetry. You cannot get rid of all the degrees of freedom of your metric. You get extra stuff. But actually, it's possible to compensate for these problems by giving some funny profiles to your dilaton. There are some things like called linear dilaton backgrounds, where you can actually make a string theory which lives in less than 26 dimensions at the price of having some peculiar behavior of the fields. These are called non-critical strings. Usually not very important. It's what mentioned they exist. Now, okay, so what we've seen is that it's pretty much straightforward to have strings moving in the background of some classical geometry. The geometry has to be dynamical, has to satisfy the equations of motion, and this geometry can be interpreted as excitations of your string fields. Now, perhaps I can use the last 15 minutes optimistically of the lecture to start describing a situation where string theory extends the notion of geometry. So here, pretty much I had in the back of my mind, starting from flat space and changing the metric a little bit. Okay? Putting some background for the metric, maybe some gravitational waves coming in, something like that. But what if the change in the space-time is a bit more dramatic? What if we introduce some compact direction, for example? So I would like to start discussing how string theory would look like in the presence of some compact directions in space-time. And for simplicity, let's just take a space-time which has a circle inside. So we'll take a space-time which, instead of being R1,25, is, say, R1,24 times the circle. Because this is still flat, we'll be able to do everything by using free field theory on the worksheet. So that's good. But still, there will be quite interesting new effects. So what does this mean? Okay, it means that out of my 26 scalar fields to describe the motions in space-time, I want to take 25 and treat them in the usual way, and take another one and make it compact. So identify y and y plus 2 pi r. So what happens if I study a free theory of a compact scalar? I'm still going to have the same action as before, saying conformal gauge, something like that. So I can still do everything by path integrals, for example, or just by the usual first quantized formalism. The difference is the same. My path integral will be path integral over all the configurations of the field, which makes sense up to this identification.
So if I can compactify one of the dimensions, that allows me to expand my field in Fourier modes, and that will introduce mass terms, right?
Yes, so there will be Caruso-Klein modes.
Yeah, exactly. So those are, I mean, when I have a mass term, then I have, scaling invariance.
Mhm.
It shouldn't like violate the conformal invariance of my theory.
It's a mass term in space-time,
Oh, okay,
not on the worksheet. This is still a massless free scalar in 2 dimensions. So we can just do our usual, if we want to study the problem on a cylinder, we can do our usual Fourier expansion. The main difference is that because of this identification, nobody tells me that the scalar field is going to come back to itself when I go around the cylinder. Basically, can come back to itself after a shift. So I need to allow the possibility that the scalar field will have some winding around the cylinder. See, this way, if sigma goes to sigma plus 2 pi, the scalar field goes to sigma plus 2 pi r times w. So I want w to be an integer. So the first difference is that there is a new term. The second difference is that the zero mode itself is periodic, which means that the momentum conjugate to it must be discrete. It's like when we do quantum mechanics on a circle. So in particular, the momentum should be written like that. Okay. So the states of my scalar field on the cylinder will be built from a set of vacua which carry more than the usual labels. In flat space, non-compact, the ground states were labeled by momentum, and then we acted with oscillators to build more states. Now the ground states can be labeled by the momentum and winding. And then you can act again with oscillator and then to build a Hilbert space. And now if you compute the currents, the holomorphic and antimorphic components of the current, you see that now they get a contribution both from P and from W. So in particular, the zero modes of the currents So remember, when space.
I have one question with respect to the winding number. So you're embedding the string into space-time.
That's right.
So it's like putting a topological defect on your space-time, or isn't it?
It's more like this string is free to wind around your space-time. So if space-time is standard flat, I tend to use that one, but probably it's a bad idea for the video. So you can get particle-like things by having a string, small strings with some excitations on them. Okay, so your excitations look like a tiny string oscillating around. But if your space-time has a circle in it, you can have a string that wraps a certain number of times this circle. it will still look like a particle, roughly, from the point of view of the remaining space-time directions. But now it will have, for example, a mass, an energy, if you want, which receives a contribution from the tension of the string wrapped around the circle. So, see, this generalized the old A naught equal to P, A naught bar equal to P.
Can you just explain again how you wrote that down mathematically? Like, why is it multiplied by sigma?
I just wanted a solution of the classical equations of motion, which is periodic up to these shifts. So without this, it's just periodic, and this takes all the shifts, pretty much. So from A naught and A naught bar, I can also compute L naught and L naught bar. So which sort of states do I get from this? Well, I'll need 5 more minutes. So the string states will be now labeled by what? There will be the quantum numbers of translations in the remaining directions. Then there will be the momentum in this circle direction, which is like the Kaluza-Klein momentum, if you have met that notion. But then there will be also this strange winding. Now, if the radius is very, very large, R is very, very large, the fact that the momentum is quantized is almost negligible. And the winding modes will have very large not eigenvalue, which turns out into a very large mass. So if you have string theory in a very large circle, whatever, all the fields that you had before have been decomposed into Kaluza-Klein modes, into modes with discrete momentum on the internal circle. And you've added some very massive string modes, which come from strings wrapped in the circle. So, of course, the existence of these modes is really a sharp difference between string theory and quantum field theory. But as long as the circle is very large, you don't notice the difference. As the circle gets smaller and smaller, though, this contribution becomes definitely important. Actually, if I just stare at this blackboard and the Hilbert space of this theory, how do I distinguish momentum and winding? I have a Hilbert space, I built on some states, they have two discrete labels. They enter the stress tensor and the currents more or less in the same way.
Typically, when we say we want to label our space by something, those things have to be the eigenvalue of some operator. So which operator corresponds to?
I define an operator to be equal to W on these states. No, W itself is actually made of Y, right? So this operator is Y at 2 pi minus Y of 0. Even better, you can write it as a contour integral of the Y, right? So that M or P was the integral of the sigma, the tau X, the tau Y in the sigma, right? On the other hand, WR over 2 is the integral of the sigma Y in the sigma. So they really are kind of on the same footing. There's actually a symmetry that exchanges them. I can define a new scalar field. Okay, that was stuck. I can define a new scalar field with a property that the currents for the new scalar field are the same on the holomorphic side and opposite on anti-holomorphic side. So in terms of the modes, so I can just take the modes of my original scalar field and repackage them into a new free scalar by tilde. With the same sort of equations of motion, all the modes, the main difference is that I have to introduce a new zero mode, which by definition commutes with W in the usual way. So by hand, I introduce a Y such that e to the Y shifts W. Fine. E to the IY tilde. So this is a perfect symmetry of your theory. So the theory of a free scalar, compact free scalar, has a symmetry called T-duality. Exchanges this scalar field with the dual scalar field and exchanges momentum and winding. And sends the radius true over the radius. It's actually a two-dimensional version of electric magnetic duality in 4 dimensions. The symmetry exchanges electric field and magnetic field. Now, this is kind of striking. It means that if you start studying your string theory in a very large circle, it looks roughly what you would have gotten by putting a quantum field theory in a circle. Kaluza-Klein modes and some extra very massive stuff, which are special for string theory. But as the circle gets smaller and smaller, the massive stuff becomes lighter and lighter, and the Kaluza-Klein modes become heavier and heavier. At some point, when the radius reaches square root of 2, winding modes and Kaluza-Klein modes are pretty much indistinguishable. There is actually a symmetry that rotates them. And then if you try to make the radius of the circle even smaller, it just means that you are describing your theory the wrong way. So you try to think about it as a theory living on a very small circle, but there are actually very light states from the winding modes. And your theory is identical to the theory built on a very large circle. So if you in string theory, whenever you try to make a circle in your geometry small, a new circle pops out, which becomes large as the original one becomes small. So, so T-duality expresses the fact that geometry in string theory works in unexpected ways. As long as the curvature of space-time is small compared to the string scale, everything is more or less intuitive. It's a theory of gravity. But if you try to make the curvature stronger, if you try to make circles of space-time small enough, then the classical geometry just breaks down. String theory replaces it with something else, which sometimes can be described geometrically in some dual way. Sometimes perhaps can just not be described geometrically. Okay. I mean, T-duality is a rather interesting subject, and fun things happen when you look at several circles. You get interesting things, but we won't be able to cover it at all anymore in this course. It's a sort of weak duality. It relates some perturbative string theory in some background to some perturbative string theory in some other background. It's fun, but limited fun. The real fun is to have strong weak dualities. Dualities which relate string theory, a strong coupling with another theory at weak coupling, because those really allow you to to get non-perturbative information about your theory. Now, we won't be able to really do those things in detail because we won't be able to do much about superstrings. In bosonic strings, there is a limit to what you can do. Bosonic strings ill-defined, so you cannot expect to have deep, non-perturbative insights about it. But we'll introduce D-branes, at least, which are a basic ingredient of all interesting dualities in string theory.